Hello students, let's start the next part of our topic, electronic spectroscopy. This is also known as UVVI, that is ultraviolet visible spectroscopy. Okay, so this particular electronic spectroscopy is also known as ultraviolet and visible spectroscopy. Why they have known as this particular spectroscopy, ultraviolet visible spectroscopy? This particular electronic spectroscopy, which can be covers the region from 200 to 800 nanometer of electromagnetic spectrum. Okay, from where this particular electronic spectroscopy, it can be covers the region from 200 to 800 nm of electromagnetic spectrum. Now, in this particular 200 to 800 region, how much region belongs to UV and how much region belongs to ultraviolet? Let's just see over here, UV and visible. We will going to deal the region from 200 to 400 nanometer, which belongs to ultraviolet region, and the region from 400 to 800, which belongs to which region? Visible. Getting my term, what I want to tell you is that this particular electronic spectroscopy is also known as what? Ultraviolet visible spectroscopy. And this particular electronic spectroscopy covers the region from 200 to 800 from the electromagnetic spectrum. Okay, then the region from 200 to 400 of which region? Yes, ultraviolet region. And the region from 400 to 800 which region? Yes, visible region, that is visible region. And combining these two form 200 to 800, in the electromagnetic spectrum belongs to this particular electronic spectroscopy. Okay, then in the visible region, what will happen? A substance appear colored when the emitted light falls in the visible region. Okay, if emitted light falls in the visible region, the substance which can be appear what? Colored in the nature or colored in the nature. Okay, if it is having different color, it will show emitted light when falls in the visible region. In this visible region, the substance which is present over there, it can be appeared what? Colored in the nature. Again, this spectroscopy is used to find out what? Geometry of the complexes, whether the complex is tetrahedral in the nature or whether our complex is octahedral in the nature. We can find out by using this electronic spectroscopy. Again, next what? Because the number of bands seen in the visible region and due to the DD transition depend on the geometry of the complexes. Why it can be show the geometry of the complexes? Based on what? Number of bands seen in the visible region. Why they have seen in the visible region bands, various bands appear in the visible region? Because of DD transitions. Okay, which can be depend on the geometry of the complexes. Now this particular DD transition means what? Why the particular color of the transition metal can be present? That all things we will going to deal over here. Again, in this part, DD transition, spectra of the complexes, which is more in the d electron, usually contains more than one DD band. Okay, and this is because electron of one atom is interact and repel each other, isn't it? And as you already know, the splitting of d orbital, tetrahedral as well as the octahedral complexes. I'll tell you about the tetrahedral complexes, how the DD transition. Okay, tetrahedral complexes, it can be split into what? Yes, it can be split into E2 and T2, E2T. And in the octahedral complexes, it can be split into Eg to T2G, isn't it? And here appears ulta in the tetrahedral, E to T. Okay, here E to T. Here Eg to T2G, like that. Okay, that we will going to deal in the next part, you don't worry about it. But here you already know, here if light just passed in any particular substances, it can be split in the d orbital in the two parts. One is Eg, another one is the T2G. I am discussing about in the octahedral complexes. And when light passes, that time a particular electron present in the ground state, and it after emission it just excited and it want to go at the excited state, from ground state to the excited state, and that times particular electron want to jump from the ground to the excited, and that time color will becomes change of that particular complex. Okay, we will going to deal that all in the dd transitions part. Okay, about spin coupling, orbit coupling means what, spin orbit coupling means what, JJ coupling means what, that all we will deal. I hope you have understood about this particular electronic spectroscopy. Let me explain once again. This is also known as UV visible, that is ultraviolet visible spectroscopy. It can be covers the region from 200 to 800 electromagnetic spectrum. The region from 200 to 400 is ultraviolet, and the region from 400 to 800 is visible region. Next, when substance appeared colored when emitted light falls in the visible region, isn't it? Now next, the spectroscopy, which can be used to find out geometry. Why? It is based on the number of bands in the appeared in the visible region due to what, dd transition, which can be depend on the geometry of complexes. This is about what, electronic spectroscopy. Now the next part we will going to deal about colors of transition metal ions. The aqueous solution of transition metal ions are differently colored. Now the question will arise, transition metal ions means what? As you already know, here there are mainly four blocks or four particular blocks of elements are there, that is S block, P block, D and F, isn't it? And these particular elements which belongs to this particular D block elements, that particular elements we usually used to call it as a transition elements. And the metal which can be present in this particular block, that is in the D block, that we call it as an what, transition metal. Just take an example of cobalt is there, copper is there. Is it copper a particular metal? Yes, cobalt is metal, copper is metal, nickel is metal is there, isn't it? Again chromium is a metal, isn't it? So these some metals which are available in the transition itself. So that particular metal we used to call it as a transition metals, and the ions which are appeared in their aqueous states, that we call it as a transition metal ions. So the aqueous solution of transition metal ions are differently colored. Why they have different in the color? And again you can take an example of some precious gems. Precious gems means what? You already know, some stones which are colored in the nature. Usually you will put in your fingers, nicely in the fingers you'll put our ornaments, some ornaments also they are used to put some stones in that, isn't it? You can take a best example, or you can say best example of HOD sirs fingers. You can see different rings in that, precious gems are available. And again they are differently in the color, and why they have differently in the color, that we will going to deal. That particular different color due to the transition of electron from one d level to the another d level, that we call it is as a dd transition. So we can take one example or some examples of particular transition metal ions. Which are those? Just see one complex over here, the complex of cobalt complex, which is pink in color. Again you can take complex of cobalt, another which is blue in the color. Again complex of nickel, green in the color. Another complex of nickel along with amine, also blue in the color. Again complexes of chromium, okay, which is having different ionic state. One is violet in the color and another one is the bright blue in the color. Okay, this is odd. And one thing is that first the color which are present, there are some primary colors are there, and there are some secondary colors are there, and there are some tertiary colors are also available. I will tell you that all once again. Okay, so primary colors, when light emits on this particular primary color and when it passes over there or secondary D level, the secondary colors will arise. Again it can be passes in the third generation, the tertiary color will arise. Like that, different colors of the different complexes can be available over here. So the different colors are due to the transition of electron from one D level to the another D level. These are called as what? DD transitions. So different color of any elements or any particular transition elements or metals is because of transition of electron from one D level to the another D level. These are called as what? DD transitions. So the different colors are due to the what? Transition of electron from one D level to the another D level, and these are called as what? DD transition. I hope you have understood the color of different elements as well as why they have become colored instead of becoming as it is how they are. As you know already, these are the cobalt complexes. You take one example here, these cobalt complexes which are pink in color at here, but when you add it in this particular HCl, the color of this particular element get changes, and it will be pink will get changes into the violet in the nature. Okay, or else it can be changes into the blue in the color or green in the color. Why these such things will be happen? Because of the DD transition. The different colors are due to the transition of electrons from one D level to the another D level, and these are called as what? DD transition. Next, the energy falls in the visible region of the electromagnetic spectrum. Okay, and the color of the solution seen is complementary color of the light absorbed by the solution. It means what? When you see the particular elements which is pink in color, the complementary color will be different of that, or secondary color will be different of that. I will tell you that once again in the next part or next class by slideshow view. If you see the particular complementary color, mainly three colors are there, only three are there: red, green and blue, and remaining all which are there, they are all complementary with each other. When light falls on it, different colors will be available over there. The color of the solution seen is complementary color of the light absorbed by the solutions itself. Okay, these all things will happen color of the transition metal ion. It is because of what? Due to the what? Different colors is due to the transition of electron from one D level to the another D level, and this is called as what? DD transition itself. I have already told you what is the meaning of DD transitions. So next part we will going to deal this DD transition. The spectra of complex with more than one D electron usually contain more than one DD band, and this is because the electrons in an atom they interact as well as repel each other. The electrons in an atom, they interact and repel each other. Okay, you can take here example. What I am telling you, DD about DD transition. The spectra of complex usually more than one D electron usually contain more than one DD band. Okay, and this is because electrons in an atom, they interact and repel each other. You can take example here. D2 electron configuration ion gives rise to 5 different energy terms, that is 5 energetically distinct way of arranging these electrons even in the case of free ion and atom. The spectra of complex with more than one d electron usually contain more than one dd band, and this is because electron in an atom, okay, they interact and repel each other. For example, D2 electronic configuration gives rise to 5 different energy terms in case of free ion or molecules also. So D2 electron terms which will be there, it can be used what? 5 different energetically distinct way of arranging the electrons, as you already know here, isn't it? dxy, dyz, dzx, dx square minus y square and dz square. These are the 5 ways of arranging different or distinct ways of electron. Okay, then even in the case of free ion or atom, it can be possible. So just see here, the way in which the angular momenta associated with what? One is orbit and another one is the spin motion of electron, isn't it? What I am going to tell you is that angular moment of any electron, it is associated, one is orbit and spin motion of electron. They may be varied and there are many also, and the interaction may occur out of 3. They have given these 3, in that any one interaction may occur. In that, one is spin-spin coupling, another one is the orbit-orbit coupling, and another one is the spin-orbit coupling. Any out of these 3, any one can be occur. Okay. So what? The angular moment of any orbit, which will be the angular moment, or any electron which will be there, it is just associated with, one is orbital spin motion and spin motion of electron, and they can be may varied as well as there are many also, and the interaction may occur. What I am telling you, the interaction may occur out of these 3, any one, that is spin spin, orbit orbit or spin orbit. Okay, there are mainly 2 principal coupling schemes are used. In that, first is there RS coupling, Russell-Sanders coupling, and second one is there JJ coupling. Okay, these 2 principal coupling schemes are mainly used. In that, first one is there, that is nothing but Russell-Sanders, that is RS coupling which will be there. It is applied, or I will tell here, coupling. First we will going to dealing this. This particular scheme is applied to configurations of, so Russell-Sanders coupling scheme is applied to the configuration of atoms or ions where electronic repulsion is much stronger than the magnetic effect. Getting my point? RS coupling which will be there, this particular Russell-Sanders scheme, it is applied to the configuration of, you know already, electronic configuration 1s2, 2s2, 3s2, isn't it? That particular configuration of atoms and ions where electronic repulsion, the electron get repulsed from one another, is much stronger than what? Magnetic effect. That is, or it is assumed that where spin-spin coupling is more favorable than that of orbit-orbit coupling, it is more favorable than that of spin-orbit coupling, isn't it? Getting my point? What I want to tell is that RS coupling, there are mainly 2 principal coupling schemes can be used. In that, first is there RS, another one is there JJ, and here RS coupling which will be there, it is applied, mainly applied, this particular scheme is applied for the configuration of atoms and ions, or ions where electronic repulsion is much stronger than that of what? Magnetic effect. That is, assumed that spin-spin coupling is more favorable than that of orbit-orbit, orbit-orbit more than that of spin-orbit coupling, isn't it? This is about what? Our RS, that is Russell-Sanders coupling. Now next, what? JJ coupling scheme. Now the next term about the JJ coupling. This particular JJ coupling scheme which will be there, it is applied where opposite of Russell's Sanders. Where what we have saw here configuration of atom ions where electronic repulsion stronger than the magnetic, but in the JJ magnetic stronger than the electronic repulsion. Just to see here, JJ coupling scheme is applied where magnetic effect acting on an electron of configurations are stronger than that of inter-electronic repulsion effect. This is about our JJ coupling, isn't it? Exact opposite that of RS coupling. Next part we will going to deal what is the meaning of spin-spin coupling, orbit-orbit, spin-orbit. Spin-spin coupling, S resultant spin quantum number for a system of electrons. The overall spin S arises from adding the individual ms. Okay. Then together and as a result coupling of spin quantum numbers for the separate electrons. Next, orbit-orbit. The total orbit angular momentum quantum number defines the energy state for a system of electron, and this state or atoms terms the letter represented, that is S, P, D, F, G, H as like that. Isn't it? And then spin orbit means what? Coupling occurs between the resultant spin and orbital moment of an electron, which gives rise to the J, the total angular momentum quantum number, and multiplicity occur when several levels are close together and is given by the formula 2s, that is 2s plus 1. Okay. This particular, the Russell's Sanders term symbol result from this consideration given by 2s plus 1 and again here L about spin orbit. Okay, or I will tell you one example over here. For D1 configuration, S is equal to plus half, isn't it? Here 2s plus 1 is equal to 2L is equal to 2. Isn't it? And the ground term written is in the form of like this. I will tell you this all once again in the next class, but then also I will tell you once again the definitions of this all. The spin quantum number for a system of electron, ore of spin arising individual ms, isn't it, together, and as a result coupling of spin quantum number for a separate electron, that we call it as a spin individual spin quantum numbers or individual spin quantum numbers simply we are supposed to add over here, then it will happen spin coupling. Then orbit, yes, L, the total orbital angular momentum quantum numbers, which can be defines the energy state of a system of electron. It can be represented as P, D, F, G, isn't it? Orbit, you already know S orbit, P orbit, D orbit, like that. Next, spin orbit nothing but coupling occurs between the resultant spin and orbital moment of an electron, which gives rise to the J, total angular momentum quantum number. Okay, these three definitions we will go into once again in the next class. Let me revise once again the what today we have studied. In that first we have studied about electronic spectroscopy means what? This spectroscopy also known as ultraviolet visible region from 200 to 800, in that 2 to 400 ultraviolet, 400 to 800 visible, and the substance which can be occurred colored when light emitted in the what? Visible, and again it can be defines the geometry of the complexes. Color of the transition metal ions. The aqueous solution of transition metal ions are differently in the color, as we already know here. 4 blocks S, P, D, F, and in the D block transition metals are available, and that transition metals which are colored in the nature, colored is because of DD transition. I have saw here some complexes of cobalt pink and blue in color, complexes of nickel green and blue in color, complexes of chromium violet and bright blue in color, isn't it? And what is the DD transition we have saw? The different colors is due to the transition of electron from one D level to the another D level. This is called as what? DD transition we saw. The energy falls in the visible region in the of electromagnetic spectrum here. And the color of the solution C complementary color to the light absorbed by the solution, isn't it? That we have saw today's part. Next we saw about DD transition. The spectral complexes with more than one d electron usually contain more than one dd band, and this is because electron in an atom, they interact and they can be repel each other. Example D2. D2 is nothing but what? Ground term return for D1 configuration. Isn't it? It gives in the 5 different energy in case of any elements or any ions or any electrons. Next we saw about Russell-Sanders coupling. So what is this particular Russell-Sanders coupling? The way in which angular movement associated with orbital and spin motion of electron. They may vary different ways and they may be varied. And the interaction may occur out of these three, that is spin spin, orbit orbit and spin orbit. Okay, so these three interaction may occur over here. There are mainly two principal couplings. One is Russell-Sanders and JJ. So what is Russell-Sanders RS coupling? This particular scheme is applied to the configuration of atom or ion where electronic repulsion much stronger than the magnetic effect. Where, or that is we can say, spin-spin coupling which is more favorable than that of orbit-orbit, and orbit-orbit coupling is more favorable than that of spin-orbit coupling. Now the next term JJ coupling, which is exact opposite to that of this. It is applied to the configuration of atom or ions where magnetic effect is much stronger than the electronic repulsion. Just to see here, JJ coupling scheme is applied where magnetic effect acting on electron of configuration are stronger than inter-electronic repulsion effect. Okay. So in the now next class what we will going to deal, spin-spin coupling, orbit-orbit coupling means what, spin-orbit coupling means what, definitions, Hund's rule we will going to study. Okay, and graphical method for the determination of a ground term, okay, for free ions. And next we will going to deal about what, terms for 3D and free ion configuration we will going to deal, isn't it? And number of quantum state, how to calculate, that we will going to deal in the next class. Okay, and today we will stop here itself. Thank you.